Our next speaker is Łukasz Daniluk. Łukasz is a software engineer at Intel Technology Poland for almost 5 years, where he has done various projects revolving around Linux, including graphics compute software libraries, software for many core processors, and fabric networking. At work, he does code reviews as a hobby and has a particular interest in all things parallel. When not at work, he takes care of his Samoyed dog Ragnar and plays any games that he can get his hands on. Today, he's going to talk about reducing OS noise using offload driver. Please, a huge round of applause for Łukasz Daniluk.
So hi, my name is Łukasz, as already introduced. Pardon me any stutter, it's my first presentation in front of a bigger audience. Today I will talk about a little project that we did a few months ago on reducing the OS noise. So what is this OS noise? So the noise, as we often hear, is some irregularities. It's something that is not desired, it's something that interrupts us, something that interferes with our work or with our hearing, for example, even. These irregularities in computer science can be, for example, interruptions from the various computer parts or from the timer, for example. And timer interrupts are one kind of interrupts that are always run on your processors. So you can imagine processor doing some work from time to time, even when you don't want them to. So there was this idea to create something like tickless kernel, where some mechanisms are disabled, some mechanisms are altered, and it all allows computer to perform at a bit higher rate with a bit higher performance. Nevertheless, this doesn't remove all the interferences from the operating system, so sometimes you have to disallow operating system from running the application on this particular course in order to gain a percent or two of performance. And when you hear percent of 2 performance, it doesn't really strike you as much gain, especially when you have to do a lot of work to gain these percents. But when you see a single computer with, for example, 6 cores, 8 cores, 2% per core is a bigger deal than on a single core, since you can have almost 15% increase of performance, provided it increases linearly. But in data centers, where you have thousands of nodes and each node has any number of cores ranging from 48 to 80, then you see the gains, not only in terms of performance, but also financial gains resulting from the increased performance per dollar invested and less energy consumption. So we had an idea. There is a many core architecture from Intel called Intel Xeon Phi, and these processors have a lot of cores, and by a lot I mean up to 70 cores per CPU. And we decided that we'll hide some CPUs from the point of view of operating system. So when we will boot our OS, it will have no idea that it is running on a computer with that many cores. However, we had to set some limitations to our solution in order for it to be achievable. So the memory space that we'll be using between host cores, and host cores will be the term for cores visible from the point of operating system, and hidden CPUs will be the same. By the way, I'll be probably using term processor, CPU, and core interchangeably, so for the purpose of this presentation, all of them will mean the same. Another thing we wanted to reach was that we will not make any modifications to Linux kernel. Since we're all Linux developers, Linux was our platform of choice. And then, in order to measure our solution, since we tried to get performance improvement, and in order to get performance improvement, you have to do measurements both before and after modifications. So we decided to model our library in order to provide a DLP approach that is data level parallelism. So we are parallelizing data in order to run the same algorithm that was doing essentially the same work on all the cores, but working on different parts of the data. So we follow up with the proposed architecture. So on the top, in the top we have our user application, And this application is something that user writes, of course. It had to communicate with our runtime library. So runtime library is something we also deliver in order to make application of the user communicate with the driver. And why is that so complicated? So from the level of runtime library, we do not really have access to low-level functions of the Linux kernel, but we had the access from the driver module that we could create. And we opted for the driver in order to enforce our policy of not modifying Linux kernel directly. It is a bit of a stretch, but I will follow on that in a moment. And the driver itself is responsible for all the operations that involve the hidden CPUs, as we call them, and exposed or the host CPUs, as we have on this diagram. And we can see that Linux kernel only should interact with these exposed CPUs and do not touch hidden CPUs, and that was the case. So, in order to launch our solution, at the very beginning we used some emulation software in order to test our program, because as we heard in another presentation, rebooting servers takes a lot of time, and more often than not, when we did something wrong, it caused a reboot or loop of reboots. So we came up with the solution that we could set up on a physical environment. And here comes a little stretch, because in order to hide the processor from the operating system, we had to modify what the BIOS reported to operating system, because operating system gets its information from the BIOS tables, from ICPI tables, in particular one called MADT. And we had to remove the IDs information on these CPUs from this table, and then this table had to be somehow fit into the operating system. So Linux kernel has this initial image and inrd, and you can put the ICPI table image in there, and it will load it instead of one from the BIOS. So we modified the image file, but not the kernel code, not at all, and booted the kernel with the modified image. It allowed us to hide the CPUs from the operating system, and that was just the tip of the success, because we had to load the driver and actually boot the cores. And when we tried to boot this cores, of course, we had no information from the BIOS on them. So here's suddenly a manual part, and we had to feed the APIC IDs into the driver. APIC IDs, as name says, is an ID, so something that uniquely identifies CPU inside our system. And when a user wanted to use our library, the workflow is like with your usual library. So firstly, you had to initialize the runtime. It did some communication from the driver. And by some communication, I mean we mentioned that we were doing data level parallelism. And it was a simple solution. So the CPUs were reserved for the particular process, for the use of particular process. And initializing the library was kind of reserving the CPUs for sole use of our user space application. Then after the CPUs were reserved or were waiting to be reserved, they started executing the idle loop. And the idle loop was waiting additional data and additional functions from the user space application, which were passed in form of pair of pointers. So pointer to a function that was working on the data, and pointer to a data that was split between all the reserved cores. And after we used our runtime, there's a process underneath. And this process ongoing underneath is called the offload. So we offload the work from our host CPUs, from visible CPUs to the OS, onto the hidden ones. So application has these all values for the function called moved into the hidden CPUs, and the hidden CPUs fetch this work from the memory and run it, and it happens without any interaction from the OS, because it's a simple function with some kind of exit criteria. The function operates only on the data is provided by the user. So there is nothing that has to be done from the point of view application. When the work is done, there's mechanism on Xeon Phi that allows CPU to go into a state of sleep with M-wait instructions, so there's no need to go into kernel to do that. And we can support both synchronous and asynchronous function calls with this mechanism. So the example of usage of such runtime requires slightly modification of the user application, more severe than with, for example, OpenMP, but still it's kind of bearable. So first you initialize the runtime, then you run your function on the runtime, and then you call an exit function. We had experimented a bit with mechanism of destructors, but we've settled for exit function in order to deinitialize the work that was put into the hidden cores. And I skimmed through the performance setup. So it was tested on your regular disk machine with almost 200 gigs of RAM and 68 cores in order to launch state-of-the-art floating point algorithms. So we used something that's called stream benchmark, and stream benchmark is a thing that tests, basically it's used to test the bandwidth of your memory. But we tried to experiment with the potential performance gain by using different configurations for Linux kernel. Mind that we weren't recompiling the kernel, but changing the runtime options kernel was compiled with optimal options for this setup. So first we tried to disable the interrupts. Then we also disable the CPUs from the point of view of scheduler, so scheduler doesn't run any user's pace jobs on the CPUs. Then we try to modify the stream a bit. The modification was done in order to better allocate a memory. And then we tried to experiment with our runtime, and we had runtime in two versions. First version of our runtime was to use CPUs on the host machine visible to OS. And the second version, where you can see a little improvement, there is additional noise reduction in completely hiding these CPUs from the OS. The stability of our solution was quite satisfactory. We always achieved better results than on the host machine. And it was quite an achievement for us. And as with all early implementations, there were limitations. So we couldn't handle page faults properly. We had always to have memory that was backed by physical pages already. And another requirement was that this couldn't change during the run. Another thing was that the system calls couldn't be called from the computation kernel, whereas computation kernel is the function that user passed to our runtime. It is because of that there was no kernel running on this host, on the CPUs mainly. And in order to provide stable runs, we had to provide synchronization between host and driver. And it was required to be custom synchronization because constructs already available in kernel used some mechanisms that were inoperable with our hidden CPU solution. So basically, it works, it compiles, you can use it, the solution is stable, but it works on x86-64 only and was tested only with Xeon Phis. It performs quite well, but we could still optimize it further because we didn't really touch our scheduler in depth required for that. We could try to improve scalability because we didn't run it on all the cores, but disabled some cores from the for the OS. We left some cores for the OS. We should tackle these limitations in future versions. And most certainly benchmark something more complex than simple stream benchmark. And why I was saying we instead of I, because we are working as a team of 6 people. Grzegorz Andrzejczyk, who is here in the crowd with me, and Łukasz me, Łukasz Daniluk, Paweł Karczewski, Jarek Kogut, and Krzysztof Góreczny, who all of them, we wouldn't do this ourselves without the support of all of us. And with this slide, I would like to thank you for your attention.
Big round of applause.